In complex analysis, one of the things that you will need to always do is talk about analytic function. And for an analytic function, it's basically at a point, if I say that, oh, is this function analytic at a given point? It means that that function must be differentiable at that given point and in a certain neighborhood around that point as well. But that's not really what I want to discuss in this video. I want to talk about a necessary condition that an analytic function would have to pass. This condition is necessary, but it is not sufficient. So take note of that. So if you are given a problem and you have to show that this function is analytic, then you don't just go ahead and say that it satisfies the Cauchy Riemann equation. No, you don't do that. What you need to do is that you need to show that it is differentiable at that point and in the neighborhood around it. But if you want to use the Cauchy Riemann equations, you have to show that these partial derivatives, they are actually continuous. They are continuous. So that is when it becomes sufficient. So necessary condition is that the analytic function must satisfy the Cauchy Riemann equation. So let me show you how. Let's see whether this particular function f of z equals sine z, where z is a complex number. So z is a complex number. It's not a regular sine of any normal angle. It's a complex number. So, and you know that general representation of complex number, we have z equals x plus iy. So where I is the square root of -1. So I believe you should be familiar with that. We want to show that we want to write this thing in terms of, so let's go get into it. So we want to write this thing f of z in terms of u plus iv. So we are redefining this complex number since it's a function now, a function f of z. So instead of writing it as just ordinary sine z, which is what we have here, we want to be able to get the imaginary and the real part. So the imaginary part is the v, which is the one that has the I with it. And the real part is the one that has no I with it. Just like the argument itself, which is z, that is the argument of the... Anyways, I need to be careful the way I use argument in this place, because argument, when it comes to complex number, it also kind of mean a special thing entirely. But what I mean by argument here is the what the function is acting on. So z is a complex number x plus iy. It has a real part and imaginary part. So that is as a number. But as a function, f of z also has its real part and its imaginary part, and which will be labeling as u and v in this place. So the first thing is that I'm writing my z as x plus iy, as you can see that. Then you apply your sum rule for sine. You know, sine a plus b is sine a cos b plus sine b cos a. So this is what I'm applying here. So that will be sine x cos iy plus cos x sine iy. So this is just me applying the sum rule. Now, you can see the table at this right hand side here. This table is it comprises of how hyperbolic function relate with normal trigonometric functions. So you can see sine ix equals I sine x. So sine, this is the hyperbolic function of sine, and so you can see in this table. So cos iy, based on this, cos iy would then be, so you can see that cos ix is just cos x without any I. So this is going to be sine x, nothing is happening to that one. Cos iy will be cos y. Then plus cos x will still remain itself, but sine ix in this place is I sine x. So sine, that means that sine iy will become I. So the I is at the back here, then sine y. So you can always check this table out if you need any further thing. So now this has been written in form of the real and imaginary part. So the real part of this, which is our u now, this is our u, and then the imaginary part, this is our v. Mind you, when you're writing the imaginary part, you don't need to put the I. It is the guy that is standing with the I that is the imaginary part. So the moment you add the I again, you are now producing another complex number. The real and imaginary part, they are real numbers. Just that when you group them together and you write them as a complex number, that is when they become a complex number. So let's proceed. So I'm writing this out now. So u is this first guy, v is this second guy. Now, so the next thing we need to know is that we need to get all the partial derivative. So u is the function of x and y. I'm going to be getting the partial derivative of u with respect to x and with respect to y. I'm going to be differentiating v with respect to x with respect to y as well. So starting with u here, I have cos x, I have sin x cos y. Since I'm differentiating u with respect to x, that means that anything that involves y would seem like a constant. I don't need to differentiate it. So I only need to focus on derivative of sine x, which is cos x, then cos y just follow. You know, when you're doing partial derivative, you can as well just assume that this is a constant, like this is like 3 sine x. You know, if you want to differentiate 3 sine x, you have 3 cos x. So this cos y is a constant because your derivative, your change is observed with respect to x and not with respect to y. So that is exactly what why that differentiation is like that. So let's proceed. Let's do partial derivative of u with respect to y. So things change now as we have sine x cos y. Sine x will be like the constant. So cos y, the derivative is sine y. I know most of you are familiar with the fact that if you differentiate cos x, it should give you negative sine y. I know that's what most of you are familiar with. But when it comes to the hyperbolic function, the sign, they don't have any form of that sign oscillation. Cos y, derivative of cos y gives sine y. Derivative of sine y give cos y. So that is why this one is not having a negative sign. So let's proceed. Then v now with respect to x, so cos x, derivative of cos x is negative sine x, so that is here. Then sine y is just repeated since it's a constant. Now let's do for the derivative of v with respect to y now. So we differentiate sine y, and it gives us cos y. Then cos x just follow. So let's now see if this satisfies the Cauchy Riemann equation. According to the Cauchy Riemann equation, I think I'll just copy it and paste it down there. So let me just paste it down here so that we can look at it together. So this is saying that partial derivative of u with respect to v, partial derivative of u with respect to x must be the same as the partial derivative of v with respect to y. So when you do that matching, so you see that these guys, they're actually the same thing. So the first equation has already been satisfied. Partial u, partial x, partial v, partial y, they are the same thing. So first equation satisfied. When we look at the second equation, it says that partial derivative of u with respect to y must be the negative of partial derivative of v with respect to x. So when you look at that, partial derivative of v with respect to x is just the negative of what partial derivative of u with respect to y is. So this is also, satisfied now. So hence, we have been able to show that the function f of z equals sine z, where z is a complex number, satisfies the Cauchy Riemann equations. It satisfies the Cauchy. Now, is it analytic? I know I can answer that based on the fact that I have done the proof already before. But for the purpose of this video, the only thing I can tell you that it satisfies the Cauchy Riemann equations. Is it analytic? That is left for you to determine. But for this video, you cannot determine if the function is analytic or not. You have only been able to show the necessary condition, but this necessary condition is not sufficient. If you have any math concept you want me to make a video about, drop it in the comments.